Hello students, so in this lesson we will study the application of analogy to the closed frames. It's solve a problem related to how to analyze the closed frame using the column analogy method. Okay, it's almost similar to your normal frame, symmetric frames. Okay, but there is a slight difference. Now, this is the problem given to us. It's a rectangular closed frame. So, the length is 6 meters, the height is 4.5 meters, and the loading condition are like this, as you can see. So, let us name this as A, B, C, and D. Now, if you observe, this closed frame is a indeterminate structure. So what we have to do is we have to convert this into a determinate structure. So whenever you want to convert a closed frame into determinate structure, you have to give a cut in any of the member. And wherever there is a cut, what you should do, one portion of the cut you have to put it as fixed end, and the other portion of the cut you have to give it as a free end. Only that is the difference. After that, the entire step will be similar to the analysis of frames, how we have done in the previous problem. Okay, so first is to what? To make the structure into a determinate, basic determinate structure, for which I am giving a cut in the member CD like this. Okay, so this is the roller. So the roller is like this. So this is where I am giving the cut, this portion. Now this became a basic determinate structure of a closed frame. Understood. Now what is the loading? Loading will not change. It's 120 kilonewton, and here it is 40 kilonewton. Right. Now what shall we do? We shall draw the free bending moment diagram. Okay, I'll change the color. So we are now drawing what? Free bending moment diagram. See, this is the original closed frame. This is what? BDS, basic determinate structure. What is this? Your free moment diagram. Let us call this as M1 diagram. Okay, so here the loading is 120 kilonewton. Now if you want the moment at this point B, what is it? 120 into 2. Right. So how shall we draw it? We shall draw it like this. So that's 240 and 240. Then coming to point A, if you want the bending moment, what will it be? 120 into 2 clockwise, that's 240, plus 40 into 3 clockwise, that's 120. So 240 plus 120, it will be what? 360. Okay, so these are all straight lines. So this is 360. Then so this is your 360 and this is your 360. So M1 or MS diagram we can tell it. This is figure A, this is figure B, and this is figure C. Now once you draw your free bending moment diagram onto the structure, we have to draw the analogous column. Right. So how will our analogous column look? If you observe, for the vertical members, that's AB and CD, it's 2EI, and for horizontal members, that's AD and BC, it is 3EI. So your analogous column will have different width. So here we take like this. So this width is how much? 1 by 3 EI. This width is 1 by 2 EI. This also is 1 by 2 EI, whereas this is 1 by 3 EI. Okay, don't bother about the scaling. Okay, their figures are not to the scale. You just have to understand the concept. So this we'll call it as what? Analogous column. Now on this analogous column, what you need to do? You need to draw the MS by EI diagram. Okay, so this is your MS diagram. Now you need to do MS by EI diagram. So you have to divide these values by the EI values what you have. So in that case, how will your figure look? Okay, so divide it and see the values. So you will get something like this, like this, like this, and here you will get something like this. So all this I'll do one thing, I'll highlight, right? So what are the values? I will write the values here. So here this is 240. So 240 by, so it will be 120 by EA. Here it will be what? 240 by 3. So that will be 80 by EA. Coming to this portion, it's 360 by 3. So 120 by EI. Here is what? 360 by 2. So it's 180 by EI. If you observe, this is so confusing. Actually, this is your area 1. This is your area 2. This is your area 3. And this is your area 4. So this is your figure E. That's your MS by EI diagram, but it is so confusing. So what we have to do in closed columns is convert it into a equivalent loads. Whatever loads we have got here, we can convert it into equivalent loads. So just convert these into areas. Convert these areas into the loading. Put the loading upwards because they all will create what? Compressions on the inner side. Okay, so we are putting the loading upwards. Basically, in order to avoid the repetitive calculation of load terms, equivalent concentrated loads are calculated. That equivalent concentrated loads, we'll put it here in the figure F. Okay, so we'll write it as equivalent loads. So here it is A1, that's equal to half into 80 by EI into 2. That's your 80 by EI. Right, then coming to A2, that will be what? 120 by EI into 4.5. This is rectangular, this is triangular. Okay, that's why. So we'll get 540 by EI. Then A3 here I'll write. So that's 90 by EI, and finally your A4. A4 will be half into base into height. That's equal to 360 by EI. So these are all the areas. So these are the different things which we have to calculate from the original closed frame to the basic determinate structure, then the free bending moment diagram, then the analogous column, then the MS by EI diagram. Because the MS by EI diagram is very clumsy and the loadings are overlapped, in order to avoid the repetitive loadings, what we have to do, we have to convert them into the equivalent load. That is nothing but convert those areas, convert the shapes into areas. Okay. So now after this, what we'll do, we'll find the properties of the analogous column. So if we name the steps, step A, B, C, D, and E. Now we're going for step F, that's properties of analogous column. So in which first what we have to do, find the area. Okay, very simple. There are two, these two are same and these two are same. So what I can do is 2 times of 1 by 3 EI into 6 is for the horizontal portion, and then plus 1 by 2 EI into 4.5 is the height. This is for the vertical portion, right? So that's your total area, 8.5 by EI. So once I get my total area, the symmetrical axis are the centroidal axis. Here, this is also symmetric, this is also symmetric. So both the axes are symmetrical axis and they are nothing but your centroidal axis. Now we have to calculate what? The Ixx and Iyy. Remember, whenever you are calculating Ixx and Iyy, 1 by EI whole cube will come in few places. So this term is negligible. So what we can do, we can remove the entire term because 1 by EI only is very small. So 1 by EI whole cube will become still small. So we can neglect this term. So in that case, what will happen, in few places BD cube by 12 will vanish and in few places AH square will vanish. Okay. So based on that, the Ixx will be what? 2 times of. Why are we writing 2 times of? Because these two are same and these two are same. Right? 2 times of BD cube by 12. So that's 1 by 2 EI by 12 into 4.5 whole cube plus AH square. That's 1 by 3 EI into 6 into 2.25 whole square. Right. So on simplification, how much will we get this? 27.8437 by EI. Similarly, when you do for Iyy, what will you get? 2 times of, here also 1 by 2 EI into 4.5 into 3 square. Here what will happen? BD cube by 12 will get nullified, whereas AH square will come to the first portion, and then here BD cube by 12 will come, but AH square term will get vanished. So wherever 1 by EI whole cube is coming, that will get vanished. Okay, so this on simplification will give you 52.5 by EI. So this is your Ixx and this is your Iyy. So what are all this? These are the properties of your analogous column. Then next what we have to do, find the properties of load diagram. So let's first calculate the P, that is the total load. Okay. See, what are we doing? We're finding the properties of load diagram. So P is the total load. So 80 plus 540 plus 90 plus 365 here. So these are the values which I have taken now to find the total load. Okay. So this will give you, the addition will give you how much? 1070 by EI. Then you have to calculate MXX and MY. First let's do MXX. It's equal to 80 by EI into 2.25 plus 540 by EI into 0 plus 90 by EI into 1.25 plus 360 by EI into 2.25. What am I doing? The loadings into the distances for the x-axis is what I am doing here. Okay, so that will give you what? 742.5 by EI. Similarly, you do for MYY. So 80 by EI into 3 minus 2 by 3 is 540 by EI into 3 plus 90 by EI into 3 plus 360 by EI into 1. Perpendicular distances. These are for the YY axis. Okay. So it will give you a value 246.667 by EI. So that's your MXX and MYY. Now after this, what we have to do? We have to do the final calculations, final moment at point A, B, C and D. Okay. So now very important is formula. Okay. So in the previous problem when we did symmetric portal frame, we found MIA, MIB, MIC and MID. So for that we need to use the formula. What is the formula? PIA. For example, if you are taking point A, it will be P by A, that's load by area, plus YY by IYY into X plus MXX into IXX into Y. So this is very important. In the previous problem, I have not written this formula. So you please reconsider this formula and do it. Okay, I have directly shown you how to do it, but I have not written this formula. What you can do is you can add this formula if you want for easier remembrance. Okay. So now in the case of closed frame, we get 4 values like this. So what I'll do is I'll create a table for us. Let's create a table now. Okay. Let us write point MS, then P by A, then MYY by IYY, then MXX by IXX, then M, then MF, final moment. Okay, so points are A, B, C and D. MS, we have previous diagrams, if you observe, we have all these values. Okay, so that will be minus 360, minus 240, 0 and 0. Then P by A will remain same for all the values, minus 125.88. Where's your P and A? See, this is your P. Okay, this is your A. So that P by A will be constant for all the places. Then MYY by IYY. Here you have it. MYY, IYY. Right? So if you substitute, calculate minus 139.24. It's same everywhere. Then you got your MXX by IXX. Here it is minus 60.00, 60.00, 60.00 and minus 60.00. 139.24, let me write full. 139.24, 139.24. Then we got to calculate the value of M. We should be very careful with the signs. Okay, because based on that only you will get your final result. So that will be minus 325.12 minus 205.12, 73.36 and minus 46.64. That is your M. Then you get your MF. MF, how you will calculate is, it is your final moment which you have to calculate, minus 31.88 minus 34.88, then minus 73.36 and it is 46.64. So how will you get this? You will get this equal to MS minus M. M. Okay, so let us call this as MIX. IX. This X will vary as A, B, C, and D respectively. So here I'll call it as IX. So this is your formula for MF. That's your final moments. That's how you calculate the final forces in the closed rectangular frame. And this is how you will do the problem using your column analogy method. Okay.